Hello everyone. Thank you for giving us the time today to introduce to analysis method of Perovskite Solar Cells by Toray Research Center. I'm Tsukasa Koyama, and in charge of TEM analysis for solar cells. Today, I'll talk to entitle Analysis Method Proposal toward the High-Efficiency Perovskite Solar Cells. Feel free to reach out if you have any concerns or questions about my presentation. I would now like to share an overview of the Toray Research Center, TRC. TRC is an independent analytical division of Toray Industries Incorporated. It was established in 1978 to support customers in the R&D and industrial fields with accumulated know-how and highly experienced experts. Our customers are not only within the Toray Group, but we also provide services to more than 4,000 private companies, universities, and national projects all over the world without advanced technologies and proven results. We offer more than 50 different analytical methods to provide tailored analysis to help customers solve their R&D and production challenges. To meet customers' needs in various fields, TRC has an extensive range of technologies ranging from physical property measurements to compositional analysis. Importantly, the technology and services are not limited only to one field but also available on any fields needing analysis. TRC mainly targets the following 6 areas. The following shows a timeline of TRC advanced technology and equipment acquisition and implementation. The upper row shows examples of first-in-the-world technology adoption by TRC, and the row below show first in Japan. Most recently, we have introduced the world's first hybrid stem that can observe even the atoms of carbon. Since its beginnings, TRC has always continued to introduce state-of-the-art analytical equipment and technology to provide advanced services to its clients. Now here's the main issue. In perovskite solar cells, PBI2 formed on the surface plays an important role. The reason for this is that PBI2 has a larger band gap than perovskite band gap and thus acts as a passivation. This is demonstrated in the measurement examples on the right. X-ray diffraction XRD results shown in Figure A. For sample A, almost all diffraction peaks were originated from perovskite phase. Only a weak PBI2 diffraction peak located at 12.6 degrees was observed. Strong PBI2 diffraction peak for samples from B to D confirmed the obvious existence of PBI2, and the diffraction peak of PBI2 is even stronger than that of perovskite for sample D. UV-Vis absorption spectra results shown in Figure B. It was also found that the PBI2 content in perovskite layer influences the absorption and also the band gap obviously. Emission and external quantum efficiency EQE observed shown in Figures B, C, and D. The blue shift of absorption could be due to the passivation of defects in FAPBI3 by PBI2. Time-resolved photoluminescence TRPL results showed that the lifetime of FAPBI3 was also significantly increased from 110 nanosecond for PBI2 deficient sample A to 529 nanosecond for PBI2 rich sample D, indicating that PBI2 actually passivate the perovskite defects significantly. We can see that PBI2 plays key role in perovskite solar cells. Therefore, the purpose of this presentation is to clarify what is happening during the heating process and the distribution of PBI2 by surface and cross-sectional observations. This presentation is talked about 5 topics today. First, we present a case study of the evaluation of gas emissions during heat treatment. Next, we will present a case study of depth profile of the constituent elements in the film. Third, from the surface, the morphology of the perovskite layer was observed by surface SEM and crystal structure was analyzed by XRD. Fourth, the spreading resistance of the perovskite layer will be presented. Finally, we will present a case study of the evaluation of the distribution of these crystalline structures. The analysis methods shown in the contents are divided into focus points, and are schematically shown in the following table. First, the gases evolved during heating are evaluated by TPD-MS, and the elemental distribution in the sample is evaluated by dynamic SIMS and GCI-BTOF SIMS. For all 4 measurements,